It's great to be back at LSU. I'm going to be giving 3 talks. So the first one will be about character varieties. But I'm using the whiteboard for the first time. So I like John better. So some definitions, properties, and examples. But in order to understand and compute the A-Polynomial, you need to know something about character varieties. The second talk will be some definitions and examples of A-Polynomials. And the third talk, I plan to give some geometry of the A-Polynomials. And in between, there are 2 sessions where we can do some examples and more computations because unfortunately, unlike the polynomials you've been computing, these polynomials get quite long and nasty, and writing them on the board can consume a lot of time. So we have time for computations, so it will be much easier if I just hook up the computer and show you online. But I'll do some things and show you and tell you, give you a recipe to do the computation. Let me just start with a few algebraic definitions about varieties and algebraic sets. And everything I'll be talking about will be over C. If you take a set in some Cn, this is an so if you have a subset of Cn, so V is an algebraic set if it is a zero set of polynomial equations. If it is the zero set of polynomial. Since we are in n dimensions, so we would have polynomials in n variables. So everything what goes on around in this side is everything is polynomial. Zero set of polynomials. And V is irreducible if it cannot be expressed as a union of 2 proper subsets. So V is irreducible if it cannot be expressed as a union of 2 proper subsets or 2 proper algebraic sets. And so just a note that if you have any algebraic set, you can always decompose it uniquely into union of irreducible algebraic sets called components. So this follows from the Hilbert-Basis theorem. So V is always V1 union up to Vn, where each Vi is irreducible. And a variety, an affine variety, is an irreducible algebraic set. So what, the nice thing about a variety is you have a coordinate ring of every algebraic set. So you have an algebraic set, and this is all going on in Cn, and there is a set of polynomials which is associated with the algebraic set. So the set of polynomials has some meaning. So whenever you have an algebraic set, you have a coordinate ring. So you have a coordinate ring. So this is the ring of all functions. F from B to C, such that there are restrictions of polynomials. Such that there is restriction polynomials. And typically you see this coordinate ring as the polynomial ring in n variables modulo some ideal generated by the polynomials on which V vanishes. So generated by the which vanish on. And what happens if V is a variety, or if V is irreducible? This implies that C of V is an integral domain. And so then we have a field of fractions. Field of fractions, which we are not really going to use it anywhere, but I just want to mention it in case it pops up. So I think that's all I want to say so far about the varieties. Any questions? Okay, so then let's define representation of variety. Now when you say representation variety, it's a little misleading because it's not typically irreducible. It has many components, but what we but for all sorts of computations and all kind of theorems, what we only consider an irreducible component of it. So that's why we look at representation variety or character variety. So if G is a finitely generated group, so let G be a finitely generated group, say with generators. And then the SL to C representation variety is defined as all the homomorphisms from G to SL to C. And this is an algebraic set. So the R of G is an algebraic set. So let me just say this. It's very straightforward to see this, and if you want, I can write more. So we have some generators x1. Well, I meant to write G1 to Gn. Sorry. So every generator. So if you take a representation, say so a representation will take a generator to some matrix in SL2C. So you get 4 coordinates for every generator. So you already have 4n coordinates. So you can see that this is something sitting in 4n, C4n. And now, because this is in SL2C, you already get a relation AIDI minus BIC is equal to 1. So you get a relation for, this is a polynomial relation for every generator. And then for every relation, you get another polynomial equation, or you get four polynomial equations for every relation. And hence it's an algebraic set.
Somehow you're using, or
yeah, I think I'm just going to say that, and you can just ask your question in a moment. So it does not matter if the group has infinitely many relations, because the Hilbert basis theorem says that every ideal is finitely generated. So even if there are infinitely many relations, you will still get a finitely generated ideal. Yes.
So back here, you didn't need to say, you said a set of polynomials. It could be an infinite set of polynomials.
It could, yeah. But the ideal generated will always be finite generated.
Will always be finitely generated by polynomials?
Yeah.
Okay.
That follows from the Hilbert basis theorem, which associates solution sets of polynomial equations and then the ideals. That's the correspondence. So then every relation gives 4 polynomial equations. Every generator gives 1 polynomial equations for SL2C. So then it's an algebraic set. So and beyond this, it's so it is really a very big set, and you cannot do much with it. So somehow we need to cut it down and get some way to handle this. Let me just put up a couple of definitions. A representation, a row, is reducible if all row of G have a common eigenspace, one-dimensional eigenspace, have a common one-dimensional eigenspace. Otherwise it is irreducible. Which has nothing to do with the irreducibility of the derivatives. And a representation, a row is abelian if its image is abelian. Irreducibility implies the representation is not abelian. But you can have, and there exists, a non-abelian reducible representations. And in SL2C, these are called meta-abelian representations. And if you have a knot, then the meta-abelian representations of the knot group in SL2C correspond to roots of non-repeated roots of Alexander polynomials. This is a very imprecise statement. There is a more precise statement, and you can see that. But somehow there's a very nice correspondence between the meta-abelian representations and the Fox calculus.
saying that's exactly the meta-Billian representations are exactly the non-Billian reducible numbers?
Yes. If you just try to even computing representation varieties, these are really very huge objects, and we don't want to even compute representation varieties. We want to reduce them somehow. So study representations up to equivalence, and the equivalence which you are looking at is conjugation. So that brings us to character varieties. And I'm going to spend all of the remaining lecture on character varieties. So we want to study representations of the conjugation. Conjugation in C. So rho and rho prime, rho equivalent to rho prime, if and only if there exists a matrix C such that rho of G is rho prime of G for all G and G. So that's what we mean. And so let me give you two definitions of character varieties. One is a definition from algebraic geometry, and we really cannot work with it at all. So we need to do a more hands-on model for the character variety. But the algebraic geometry, the definition coming from algebraic geometry is the character variety x of G is the representation variety modulo this conjugation. Now this needs to be qualified in many ways. So what does it exactly mean when I write this? So this action here, we are all convinced that this is an algebraic set. So now we are in the category of algebraic sets. The morphisms are all polynomial maps between each other. So in category of algebraic sets and morphisms, conjugation is algebraic, and so the resulting set. So you can take the quotient, and so we can take quotient. So we can quotient in the category of algebraic sets in this category, and the resulting object is also an algebraic set, and the result is an algebraic set. And the theorem of Gordon from 1868, so I'm not making this up, implies that whenever you have an algebraic group, GL and F, where the characteristic of the field is 0, then, and you're looking at invariant representations, invariant under conjugation, and when you quotient that, the resulting object is an algebraic set. So x of g is an algebraic set. But after we know this, then what? So we have really no means to do anything with this.
Is there, do you understand how if the variety is defined via ideal?
Yeah.
We know how the relationship between that ideal and the ideal for the quotient?
No, I don't know. Not for with the full representation variety. For certain subsets you can. I mean, I'm going to give you a definition where that object will be much more attractive. But I think in the general geometric invariant theory, I forget how they proved it. I have notes for a lecture where someone states this theorem. So we would let's construct an explicit model for the character variety. So we will construct an explicit model. Now the reason it is called the character variety is because the one function. So you want to look at functions on the representation variety which are invariant under conjugations. So there is one very obvious function which comes to mind, which is the trace. The trace is an invariant under conjugation. So we look at function I of g from to C. So I of g takes a representation rho to its trace. And this function is invariant under conjugation. So so what we can do is we look at the ideal generated in the coordinate ring of R of G. We look at the ideal generated by all functions of this form, and we hope that this ideal will generate the ideal for the character variety. So in short, what I'm saying is let T be this ideal generated by and no, I'm sorry. Let me just rewrite. Let T of G be the subring of the coordinate ring. Yeah, that's what. Subring of the coordinate ring of R of G generated by these functions. And we want to, we hope that T of G is the coordinate ring for the character variety. So first of all, it's not even clear whether it's finitely generated. So that's the next step is, so the next step is that P of G is generated by elements or functions I of H, where H is in the set so all products of the generators so these are 2 to the power n elements, 2 to the power n minus 1 elements. So you take traces of G1, G2, G2, Gn, then G1, G2, G1, G3, so on, and all sorts of products. And this is the proof is not very hard, and the proof is based on the trace identity for SL2C. The proof is based on trace of AB plus trace of AB inverse the trace of A plus trace of B. Let me note that we actually need much smaller generator, a much smaller generating set. So in fact we need H to be in the set S1 which is Gi, then Gi times Gj, and Gi times Gj times Gk. And how these are small, fewer elements. I think these are. So now what we are going to do is to construct an explicit model. We are going to map R of G to. So let's define a map. C to the power. Now it depends on which paper you read, so I'm just going to give you both options. If you take your n to be, so I'm going to give you both options. If you take this to be n, so you can either go to n c to the power n or c to the power p. It depends on which generating set you are using. So you define
the P
data representation.
The P that you have written down is the number of generators in S1 to the left?
Yes.
Okay.
This is just
okay.
Let me Yeah, I don't have it. I think that. So you define T of rho to be equal to T of G1 T of G versus the trace of rho of G1 dot of the trace of rho of G1 of 2 by G and 15. So now we have a set explicitly in here. So, proposition is that if you look at the image of this, that can be identified with so we have coordinates.
So your notation over there just means to go over the elements that are status or
That's right. That's right. You just take the traces. You just look at those coordinates. Yeah. Yeah. So so this can be identified with x of g, and which also implies that this is a closed algebraic set. So I should just write that, and well, this image is an algebraic set, and this is not at all obvious why this should be an algebraic set, and the proof essentially involves showing that if you look at any tuple which is given by the traces, you want to show that there are relations between these things, and these relations completely determine the set. There's a very explicit proof which is given in a paper by Gonzalez, Acuna and Montesinos. So let me just write down the paper, and I'm going to refer to that paper a lot because they give very explicit computations. If you want to, but they don't give explicit computations, they give you explicit formulas to compute character varieties. They only do one example. So the proof, the paper is this was proved by Color and Schiller in the original character variety. Representations. So they also talk about the PSL to C character variety, which I have Okay, so now we have a map from the representation variety to the character variety, which essentially takes any representation to its character, which is the trace, and this induces a map on the coordinate rings this is an algebraic map. The one thing which I haven't said anything about is I just chose a set of generators. What happens if I choose another set of generators? And if you choose another set of generators, you can construct the same representation variety, but now it will sit in a different affine space of a different dimension. But since the generators, you can write one set of generators in terms of other set of generators, you have algebraic maps which take one to the other. So there are algebraic maps back and forth. So these are all isomorphic algebraic sets over here, and they also happen to be isomorphic generating sets over here, because the trace identities will also follow the same morphisms. But here it is much easier to see the isomorphism, whereas over here it's much trickier because now you're looking at traces. For a huge class of knots and three manifolds, so all this is defined for just any finitely generated group. But for a huge class of knots and three manifolds, character varieties are non-trivial, and this is a consequence of the deformation theory of hyperbolic structures. So if you have let M be a cusp hyperbolic three manifold, and GB the fundamental group of M. So now, since M is hyperbolic, this hyperbolic structure is given by discrete faithful representation from G to the isometric group of H3, which is PSL to C. Is the group of Mobius transforms. And so PSL2C is just SL2C modulo plus or minus identity, and this discrete faithful representation, I think put the two most important items. This is a discrete and faithful representation. So as we have you saw 2 weeks ago, what this does is this makes H3 to be a universal cover of the manifold M in such a way, because this is acting by in such a way that the covering transformations are acting by isometrics. And so what that does is locally you can push down the geometry of H3 to M, and so then M gets the geometry of H3, so M gets an hyperbolic structure. And yeah.
What's the plus? Yes.
The orientation preserved.
So M is an orientable now. Is that right?
If yeah, I would. If you even if you have a non-orientable manifold, you could still give it a hyperbolic structure the same way. I don't know. Yeah, I don't think. So you can lift this representation to SL2C. Now let's lift this representation in SL2C, but not in a unique way. The number of lifts correspond to the Z2 cohomology of the manifold, and And so let us denote the character. So pick one such lift to SL to C and let chi 0 be this image in the character. And let x naught be the component containing and so theorem of Thurston says that if M has n cusps, then x naught has dimension n.
Abhijit, I have a question. So x naught, big X naught is some component of this algebraic variety.
Yeah.
Components of algebraic varieties are not necessarily disjoint. Are they disjoint?
No, not necessarily.
Okay, so how do we know that big X naught is well defined?
Take some component.
So any component. Okay. So little x naught might be in more than one irreducible component. Is my question.
Yeah, that actually is it's more trickier. It's not just that this lift is not unique. So you can actually have many x naught components. But all that really doesn't. The real key. I'm just going to make a couple of remarks about this, about why this is true. Already we know that the character varieties of hyperbolic manifolds are quite are non-trivial and large. Yes.
No, you said let x naught be a component. That's an algebraic component as opposed to topological.
Yeah.
Yes.
Yeah, that's what I was getting after.
Yes, the irreducible components of an algebraic set need not be disjoint. They can intersect in points. Yeah. Yes, so x times yeah. So okay. So a few words about this theorem. What you actually do is you prove this theorem at the level of the PSL case where you have the isometries of H3 sitting there, and what you're doing is what a lot of you saw 2-3 weeks ago. You take an ideal triangulation which actually explicitly gives a hyperbolic structure on H3 on N, and then you deform this ideal triangulation, and you can see that the deformation you can write this in terms of polynomial equations, which are essentially the gluing equations and the completeness equations. And when the completeness equations, so you have polynomial equations, the gluing and the completeness equations, which describe the hyperbolic structure, the complete structure as well as the deformed structure. And because of Mostow rigidity, there is only one complete structure. So if you look at the dimensions of the equations which are defining these the structure, you can have a dimension count and see that around the complete structure, if you let the completeness equation not be equal to 1, but if you remove the completeness equation, the dimension of that set is n. So you get a completeness equation, one equation under every cusp, and you have a family of equations. And if you impose the completeness equations, you get a discrete set. So if you remove the completeness equations, which are n of them, then you would have something with dimension n. Does that? Yeah.
I have a question. So in the case that M is a non-complement,
Yeah.
then I have just two lifts.
There is a unique lift.
Up to some.
Up to conjugation, because this is well defined up to rho naught or the conjugate of rho naught, mean complex conjugate. Oh, and yeah. When you lift, it is when it has a sign, yeah.
But see, that doesn't affect what x of
that's right.
But what about if I have something with lots of cups and lots of homologies, so I have lots of lifts? How does the representation space, how does x naught depend on the choice of lift?
It will depend on the choice of lift. But the point is but each of the character variety, the SL character variety covers the PSL character variety. So if something below is n dimensional, when you're lifting it, the components upstairs would also have to be n dimensional.
Right. So I think of x naught not as a function of m, but a function of m in a cohomology class.
That's right. This lift is actually choosing a spin structure on n, and so the lift does depend upon n and the choice of the lift. Okay, so now, okay. Now before I go to doing examples, I just want to tell you some consequences of or some methods of how the character varieties get used. Why would you study character varieties or SL2C character varieties? So I'm just going to give you a very short schematic of why people started studying character varieties, and which is called the color shading theory. So so you have M is a 3 manifold, and G is the fundamental group of M, and so you have a character, you have the character variety. Now you pick a component of the character variety and you look at ideal points of components of curves in the character variety. So by ideal points you mean points at infinity. So what happens is that every ideal point gives you a valuation on the function field of this curve. So you have some big set and you pick a curve. So now you look at some point at infinity. Now what does this point do? If you look at the little neighborhood of this, you have to think double dimension. Everything is complex. So when I draw a curve, it's actually a complex curve. So its real dimension is 2. So if you look at the neighborhood of this ideal point, well, it's at infinity, but you go to a projective model and look at the neighborhood. So when you look at the neighborhood of this looks exactly like a neighborhood in C. So and so then you look at functions from this curve to C, and these functions, some of them will vanish and some of them will have poles at this point, because this is an ideal point. Right? So because some functions will vanish or some functions will have poles at this ideal point, you can define a valuation on the function field. Right? So that's one of the reasons why we need this to be a component of the character. We need it to be a variety, so that you have the coordinate ring to be an integral domain. So we have we can complete it to a function field. right? So we have a field now, and on that field we actually get a valuation because of this ideal point. So think of this as the valuation is really very easy to write down. Suppose this is the point P, then the valuation on F divided by G, which is an element of the field of fractions. Yeah. So this is a function, this is a function, and you look at this order. So you look at. I'm not going to get this one. Look at the order of F at P. Look at this. You should really, I'm writing that from memory, so it's very high chance of being wrong. But it's essential. Think of a valuation on rational, say a p-adic valuation. So you take any integer and you look at the number of powers of 2 in it, say. And then you take any rational number and you look at the number of powers of 2 in the numerator minus the number of powers of 2 in the denominator. That gives you valuation, the p-adic valuation on rationals. So it's exactly the same thing. You're getting a valuation on the function field of this curve. Now, why is that good? Well, that gives so that gives you an action of SL2 of this function field on a tree. So this is
just. Can I ask a question?
Yes.
Back up for a second. Just if I look at F over G,
yeah.
I can write it as Z to the K times a analytic function.
That's right.
And,
Yes.
and the valuation is K.
K. That's right. That's exactly right. Yeah, I should have said that way. That's much better. Yeah. So if you have a function here, say which vanishes or which has a pole, you can write it as Z to the power K, and K is basically this number. And so that gives you an action of SL2C on a tree. Well, why is that interesting? Because you can now pull this action back. So imagine I'm on a torus board. So so now you can pull this action back, pull back this action to an action of G on a tree. So you have this action there. The pulling back action is actually very simple. It just follows from what is called a tautological representation. So that arrow is really simple. That arrow is hard. So and why is that good? Well, let's think of a very simple example. Let's think of a group which you are amalgamating along some subgroup. So you can think of this as this is something like a Van Kampen theorem. So you have like a Van Kampen theorem like thing, and you have this subgroup here, this and these two groups, and you can think of this graph. So this Van Kampen theorem like thing is going to give you an action of G on some tree. And if you look at what happens in the topology, well, there is a surface over here, and there is some part over here and some part over here. So you have your 3-manifold. If your 3-manifold group splits somehow, and this is the most simple way, splits and say you're using Van Gelder theorem to write down splitting, you can think of this acting on a tree. So, but this is a very simple tree. But in general, if you have a group action, 3-manifold group action acting on a tree, you can get essential surfaces. Amen. So, starting from the ideal points of curves in the character varieties, you can pull it back to essential surfaces. And I can just take. And this led to proofs of many theorems, among which led to proofs of the Smith conjecture. Well, actually, the Smith conjecture, the proof of the Smith conjecture started this basic idea, and there's a very nice book written by Morgan and Hyman Bass on the Smith conjecture, and it started from an observation of Hyman Bass over there, that if you have a valuation, if you have a representation, and as you have a sequence of representations going up to infinity, it gives you a valuation, and then you can pull back to an action on a tree and actually get an essential surface. And that kind of set the ball rolling. And so they proved that a lot of people contributed to the proof of the Smith conjecture, and then Collar and Shalin generalized this whole theory. And in this setup, you can see the Smith conjecture also. So they were not the first ones to prove it, but in this setup, you can see it as in a very nice way. The Smith conjecture says that if you have a periodic say diffeomorphism, then its fixed point set is a trivial knot. So periodic diffeomorphism. It is known that the fixed point set is a knot, but it was not. It was the conjecture was that it's a trivial knot. So the fixed point set is trivial.
If it isn't free, it's not.
If it has a fixed point.
If it has,
Well,
if it has a fixed knot circle.
yes. So periodic.
But for even case, you need that. Just the period.
It led to the proof of some of the newer conjectures, in particular a knot complement. If K is non-trivial knot, then S3 minus K contains an essential separating surface with non-empty mark. They prove much more, and once you actually set this up, this proof is quite straightforward. It led to the proof of the cyclic surgery theorem, which says that there are at most 3 surgeries on a 3-manifold with torus boundary, which is not Seifert fibered, which such that the fundamental group of the surgered manifold is cyclic. And
At number 2, doesn't that have to be like a non-torus knot or something like that? Non-empty boundary. Okay.
and it continues to lead more information about exceptional surgeries, which are surgeries on a hyperbolic 3 manifold which yield non-hyperbolic manifolds. So now it's time for examples, and we have run out of time as always. So let me just ask Oliver, who is taking a nap.
So, at least one example.
Yeah.
Quickly define the central surface.
An essential surface is a surface sitting inside the 3 manifold such that the fundamental group of the surface injects into the fundamental group of the 3 manifold. And there are more conditions, and it is not boundary parallel. So if you think of a surface, if you just look at like a genus 2 surface, then you're looking at curves which inject into the surface. So once you find curves which inject into the surface, you can cut them up and make the surface simple. Like if you take a torus and you take a meridian, if you cut it up, then it becomes a cylinder, and it's a simpler surface. And if you find the longitude and you cut it along both, it becomes a very simple surface. So in 3 manifolds, we want what are essential surfaces. And you cut it along essential surfaces, and the manifold becomes simple. And it was not, wasn't known if like a knotty will not condense an essential surface, and this theory gave this. There are lots of many more applications. As we'll see in the second and the third lecture, the A-Polynomial you can think of as a computational object of a computational part of the character variety. So all of these proofs actually don't compute any examples. It's just it's a machine where you put in the right ingredients, you study the right objects, which are essentially these trace functions, and you can come and you can get theorems out. So for examples, so let me just take 5 more minutes and do a couple of examples. If G is equal to Z, then the representation variety is very simple, and the trace map, which takes any matrix to its trace, and this is basically the character variety. And this is actually important because if you take a knot group, the abelianization of every knot group is Z. So if you look at the representation variety of the knot group, the representation variety of Z is going to always sit inside the representation variety of the knot group, because of the abelianization, all of these representations are there, and so same for the character variety. So for the character variety of knot groups, you are going to always have this abelian component. So this is kind of the abelian component. And even in the A-Polynomial, you will see this come up, but then of course you just learn to ignore that all the time. So there is a factor always there. If you look at the group, free group on 2 generators, so let's say if it's generated by say x1 and x2, so you look at the trace of this element. So when you have a representation, so you look at trace of x1, the commutator of x1 and x2. And so if this is the, if x1, x2, x1 inverse, x2 inverse is the identity, then we are going to get, then these representations are going to factor to the representations of C equals C. So in particular, the trace of this would be equal to 2. So if the trace of this equals 2, then so what happens is, if it's abelian, then of course the trace is 2. But if the trace is 2, then it can be abelian or it can be meta-abelian. Or so basically you get reducible representations. So you get reducible representations. So abelian and meta-abelian. Abelian representations, and so this equation, so let me just set something up. Let me say, so let me write T1 to be the trace of row of x1, T2 to be the trace of row of x2, and T12 to be the trace of row of x1, x2. Now if you just turn back to the coordinates which I put up, about the number of elements we need to generate the character variety, you will see that when the number of generators is 2, you precisely need T1, T2 and T12. So you can use this as coordinates. And this equation here, as I said, this is a trace of some word, so it should be written out in these three traces, and you can write this out. So this actually gives you an equation T1 squared plus four, and
should we be able to see where that equation is coming from?
what?
Should we be able to see where that equation is coming from right now?
If you have this equation, you can see that this is giving you this trace, but it's using the trace identities to get it. It's
okay.
Not. Okay. It is not hard, but the reference which I gave about the character varieties of group present, that has very explicit talking.
And there's a good paper by Neumann and Gold.
Oh, there is.
Oh yeah.
Okay.
That goes into great detail.
Okay. I didn't know about that. So there is another component when this is not equal to 2. So when it's equal to 2, this is what happens. But when this trace is not equal to 2, you get irreducible representations, and those are just generated, but there is no relation among these. So these are the irreducible representations, and this is just C3. Let me do one more. Well, I'm not going to do one. I'll give you a recipe to generate the equations of character varieties. The only problem is you get these words. You get these words which are basically relatives, and you have traces of these words. And then your job is to write these traces in terms of these coordinates, and that's the hard part. So you get around to it by reducing your representation variety and doing more elimination. So which I'll do tomorrow during the example session in the afternoon. Let me write on one more example. If you have a 2 generated group, and 1 related. So you can write out P1 to be a trace of row of R times x1 and the polynomial P2 is trace of row of and then the x of g is the T12 with P1 equal to 0. This is some equation in T1, T2 and P1, 2. And using the trace identities, which are quite long, as I said, you can reduce. There's the proof that you can write out any trace of any word using these elements is inductive. So you should be able to reduce this as a polynomial. And I will do tomorrow how to compute character varieties of 2 bridge knots. And there's an excellent article which was put up very recently called on character varieties of 2 bridge knot groups, which uses a different method to generate the polynomial. But similar, they're essentially looking at the words and writing down the traces as complete polynomials, but they do a lot more than that. So on character varieties, but it's on the archive by Melissa McPherson, Kathleen Peterson, and Ronald Van Look. So in theory, I have given some examples and some homework. Yeah, so let me stop here. And just as an advertisement, tomorrow for the example session, the afternoon session, we'll compute character varieties. We'll also compute some representation varieties which are smaller. So instead of taking the whole representation variety, you can take like an irreducible components or components containing irreducible representation and conjugate them to get something very much nicer, which kind of only covers the character variety like 2 to 1 map or 3 to 1 map. And then for those representations, we can compute the twisted Alexander polynomials. So we'll see twisted Alexander polynomials for representation varieties. So we'll put 2-3 things together. So thank you.
Thanks. Any questions?
Questions?
Well, like the representation variety for the free group and 2 generators, is that just SL2 cross SL2?
Yes.
The representation variety.
The representation variety.
And then
yes.
the character variety
this
is what?
This is we are looking at the character variety. Yeah. Yes.
But I mean, the character variety would just be, shouldn't we?
Well, there are the trace identities. So yeah, you have T1, T2, T1, 2. If you go down to the characters, that's what generates these. But there is also something and something vanishes. You can also get this.
Maybe you'll
Think of SL2 cross SL2. Now act on it by conjugation. That's
Simultaneously?
Simultaneously. and now make that into an algebraic set. That's what you're having to do.
But then I'm asking what it is, or maybe the answer is written there, but I couldn't interpret
Yeah,
it.
so it is so yeah. C3 union this component. So union with this equation. So this is the reducible component, the reducible representations, and this is the irreducible.
So the C3 is the traces of these three elements. And
It's
then,
just all C3, it's two,
No, there's an equation. So this is less. This is basically something like C2. We'll see another description of the representation variety of C plus C, which is not full of the most of it, because these also have this meta-abelians. There probably is a nicer way of writing this down, but I couldn't find it.
Why is it C3?
yeah, that's right.
So there are three coordinates, T1, T2, T1.
But at C3, take away the locus.
Yeah, but yeah, so you,
The conjugation should allow you to interchange them.
well, you have SL to C, which is dimension 3, cross dimension 3, and then a quotient by dimension 1. The fiber is SL to C. Is this?
Still not seeing
Okay.
You mean it should be less or it should be more?
Less. Take something out of your C3 factor.
Oh, this should be quotient.
But no, I mean, you can't have every T1, T2, and T1, 2.
Okay, we can.
Yeah.
Yeah.
Thank you.
Well, thanks again.